Hey guys, welcome to chapter 10. We are going to probably knock out chapter 10 in one video here. Chapter 10 covers acids and bases. So acids and bases fits very nicely with chapter 9 because acids and bases are very often aqueous solutions. So some sort of compound mixed with water. So that's why acids and bases fit very nicely with the solutions chapter. We are just barely going to scratch the surface of acids and bases. So we're not going to go too terribly in depth, but just kind of an introduction to them. So first thing we're going to talk about is properties of acids. So acids typically have a sour taste. So if you ever had a Sour Patch Kid, they put the substance tartaric acid on the outside of that candy to give it that sour taste. If you've ever tasted a lemon, that's citric acid. So if you've experienced this, acids have a sour taste. Acids dissolve many metals. And then acids will turn blue litmus paper to red. So very often acids are denoted with the color red, as you see in this arrow here. So there's two ways that we test in the lab with litmus paper. So we have blue litmus paper and we have red litmus paper. If I dip blue litmus paper into an acid, it will turn red. If I dip red litmus paper into an acid, it'll just stay red. So that's why acids are very often denoted with a red color. Okay. We'll look at the details of this in just a minute, but when we put acids into water, very often they will release or give away this hydrogen ion. So what we'll see for us is that acids will begin with a hydrogen. So if I go back to this chart here, what you'll see is a whole bunch of H's on the very beginning of these formulas. So that's how we will denote an acid in this class, is if it starts with an H, it's an acid. Okay, so they begin with H. And that hydrogen is often attached to a halogen, fluorine, chlorine, bromine. Remember, those are in 17 or 7A, or a polyatomic ion. So here we see nitrate attached to hydrogen, and then here we see sulfate attached to hydrogen. So just tying something that we've learned already into this chapter. Here's a chart of common acids and their names. So here we see our halogens, chlorine, bromine, fluorine, iodine. And then here we see some polyatomic ions as well. So I think this chart does a really nice job of putting it out so you can see it. It's really clear. Naming acids. So you're absolutely going to need to name acids. That's something that I'm going to ask you guys to do. So the first naming we're going to talk about is naming hydrogens attached to our halogen. So when our hydrogen is attached to a halogen, fluorine, chlorine, bromine, iodine, we're going to start with the prefix hydro. We're going to keep the base name of our halogen and then add ic acid onto the end. So for this HCl, we're going to say hydro. The base name for chlorine is chlor. And then we add ic acid at the end. So here we see hydrochloric acid, hydrochloric acid. What if it were fluorine? Good. Hydrofluoric acid. Okay. Next, we're going to name acids with polyatomics. So when we have an acid that's attached to a polyatomic, we do not start with the prefix hydro. I don't know why, but that's the biggest mistake that I see students make. So if we see a polyatomic attached to a hydrogen, we keep the base name of the polyatomic, and we either add ic acid or we add os acid. And it's really hard to say, OUS acid. And which ending do we use? Well, it depends on which polyatomic we have. So here we see hydrogen attached to nitrate. Any of the 8s will be classified as an ic acid. So the name of this guy would be nitric acid. Here we see nitrite attached to a hydrogen. Any of the ites, nitrite, sulfite. Any of the ites will be an OUS acid. So this one is nitrous acid. So this is probably the hardest thing from this whole entire chapter, is remembering that 8 is ic and ite is OUS. So it's probably the hardest thing to remember. So that's it for acids. Now let's move on to bases. So bases, they're going to have a bitter taste. So if you've ever had like a really dark chocolate, that bitter taste in the dark chocolate is from a base. It's the same bitter taste in coffee or in a wine, as sometimes has a bitter taste. So it's typically something that is you become accustomed to. It's a taste that typically people don't like at first, but the more you try it, the more you tend to like it. The reason for the bitter taste is a lot of bases are biologically not very good for you, and therefore the bitter taste is kind of an aversion, saying, hey, don't eat that, it tastes bad. Bases have a slippery feel, so a lot of your soaps have bases or are made of bases. So think about that slippery feel when you have soap on your hands. That's a property of the base. And then bases very often are denoted with a color blue because they turn red litmus paper to blue. Again, we have red litmus paper and we have blue litmus paper in a lab. If I dip red litmus paper into a base, it will turn to the color blue. If I dip blue litmus paper into a base, it just stays blue. So that's why we denote bases with the color blue. For us, bases will end with this hydroxide or OH ion. So if we click back here, these don't have it. I'll show you another slide that has it. But what we'll see is a lot of our bases will be attached to this OH ion. So that's how we'll identify our bases. And that hydroxide ion is typically attached to a group 1 or a group 2 metal. So sodium and hydroxide, or magnesium and hydroxide, or calcium and hydroxide. So that's how we'll identify bases. They'll look a lot like this right here. Naming bases. So we've actually already named bases back when we did naming in the ionic compounds. So we treated this as a polyatomic. So to name something with a polyatomic, you just take the name of the metal and say the name of the polyatomic. So this would be sodium hydroxide. If it was attached to magnesium, it would be magnesium hydroxide. So we already know how to name bases, but you'll be asked to do it again, I'm sure. So there are various definitions of acids and bases. None of these definitions are incorrect. They're just simply get a little bit more complex, and they allow for more chemicals to be classified as we get more complex. So the most basic is the Arrhenius definition, and that's what we will study in this class. So that's the furthest that you'll have to go. There are other definitions, Bronsted, Lowry, and Lewis, but we're not going to touch those in this class. Again, all of them are 100% factual. We just get a little bit more complex as we move down the list. So the Arrhenius definition defines acids and bases with respect to aqueous solutions. So right away, we can see the limitations of the Arrhenius is what if it's not dissolved in water? But for us, we'll dissolve everything in water, so we can stick to the Arrhenius. So the Arrhenius definition defines acids and bases when dissolved in water in aqueous solutions. An acid will produce hydrogen ions. So here we see our poster child for an acid. We've got hydrogen attached to a halogen, so hydrogen and chlorine. When we put that into solution, it's going to dissociate or break apart into two ions, and it breaks apart into chlorine ions and hydrogen ions. When we're looking at this definition, we're going to focus on this hydrogen ions. So I see the hydrogen ions in solution. I know that's an acid. Bases are going to produce hydroxide ions in solution. So again, I put my sodium hydroxide into water. It's also going to dissociate or break apart into its ions. And it's going to break apart into sodium ions and hydroxide ions. Again, this definition is going to focus on the hydroxide ions. So I see OH, 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 OH. I know it's a base. I see those OH ions appearing in solution. One of the things I want to point out, because you might see it in your homework or in other places that you study, is kind of building on this idea of an acid. Since this happens in the presence of water, these hydrogen ions happen to be very, 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 very unstable. So hydrogen ions don't want to stay as H plus very long. So since we're talking about aqueous solutions or water solutions, what often happens is this hydrogen will see a water molecule floating nearby, and it will essentially attack that water molecule. So it'll say, I'm really unstable like this, but if I attach myself to this guy, I'll be a little bit more stable. The big take home here is you will see this H3O written in textbooks. H3O and H plus are basically the same thing. They're exactly the same thing. This is just showing you what happens when it's in the presence of water. A lot of time textbooks don't make this connection. Me as a chemist, I just see these as synonymous, but likely you don't yet. So if you see H3O plus, just see it as a hydrogen ion. It's the same thing. Okay. The last thing we're going to talk about, and this is where we tie back to chapter 9 very beautifully, is this idea of strong acids and bases versus weak acids and bases. So very often you'll hear people say, be careful with that. It's a strong acid. So a strong acid and a strong electrolyte are defined the exact same way. So a strong acid or a strong electrolyte is something that completely dissociates in water. So it will completely break apart into its ions. So this guy right here, the hydrogen is just, hydrogen in an acid. The A is just kind of a generic term for acid. So when I put a strong acid into water, it's going to completely break apart into hydrogen ions and then whatever other anion that it is. So complete dissociation, just like a strong electrolyte. A weak acid or a weak base is much like a weak electrolyte. It only partially dissociates, or only some of the particles break apart. So again, here we've got our generic form for an acid. So the H is just the hydrogen. A stands for acid. We put it into water, and what we see is some of it will break apart into its ions, but most of it just stays together. It doesn't do anything. So again, partial dissociation, weak electrolyte, weak acid, or weak base. So looking at these two acids, see if you can determine one of them is a weak acid, one of them is a strong acid. See if you can determine which one's weak acid and which one's a strong acid. Okay. So looking at the pictures for HCl, I see a whole lot of charges here. So negative, positive, negative, positive, negative, positive, negative, positive. So everything here has broken apart into its ion. Over here, this is actually acetic acid. And what I see is just a couple charges. So here's a charged particle, here's a charged particle. But it looks like everything else just kind of stayed together. So hydrochloric acid is a strong acid. Acetic acid here would be a weak acid. I would not expect you to memorize the name of the molecules, but if I give you a picture that looks like this, I do expect you to be able to tell me which one's strong and which one's weak. That's it for chapter 10. So those are all the videos for this module. So go ahead and get started in the homework and quizzes if you haven't already. I hope you found this helpful.